So this is instantaneous center method. Here we are assuming that a link OC is rotating about a fixed origin which is O, and there are two distances which is RA and RB. Let me name this properly so that we don't have any confusions further. Let it be RA. This is A point and this is B point. So distance from O to A point is RA, distance from O to B point is RB. Now we need to find out the velocity at point A and the velocity at point B. How do we find out usually? We even have an angular velocity which is already given to us, which is omega given data. So now we find out this RA and RB by just knowing the directions first. So the direction is actually perpendicular to the link. Since it is clockwise, this arrow will come this way and this arrow will come this way. We have two values to be found out, which is VA, velocity of point A, and velocity of point B. Now, what is the logic behind it? The logic is to find out velocity at point A, we do is R times omega, and radius is usually the distance between center of rotation and the point at which velocity needs to be found multiplied by the angular velocity omega of the link. You can see that velocity is varying from point to point. As the points are coming closer to the center of rotation, the velocity is continuously decreasing. At point O, I can say that the velocity is 0. Immediately I can write here at VO, you have velocity of O is equal to 0. There is no velocity at point O, and as you are climbing the ladder, like going towards A, the velocity will keep on increasing. So I can write VA is equal to, so distance between the origin, it means the center of rotation, and the point at which we are finding out is RA times omega. Similarly, for velocity at point B, I can write RB times omega. So looking at these two equations, I can see that omega is common in them both. So I can write down omega is equal to VA by RA, and here also I can write down omega is equal to VB by RB. So from this I can just equate them both, right? VA by RA is equal to VB by RB, which is equal to omega in the end. So this is the equation which we will be using wherever we require it, okay? Wherever we require, we can use this equation. The only logic we should remember here is that you see that this is perpendicular, right? The line connecting the center of rotation and the point at which you need to find out the velocity, that is perpendicular. It means the direction of velocity and the center of rotation, the line connecting them is perpendicular. Here also the direction of velocity and the line connecting the center of rotation is perpendicular, right? So this is the basic concept of instantaneous center. Got it? We know about the center of rotation now. So now I am going to give you a diagram where you have to find out the center of rotation of different links, okay? So this is your first link. Let's say this is your second link. Done. And this is your third link. And the fourth link is the frame itself. This is the frame. This is your fourth link. Let's number them properly. Link number 1 is always the fixed link. Link number 2, link number 3, and link number 4. Now you have different points, right? So immediately, what are the points you can identify? I think you can identify this is an center of rotation. This is another center of rotation, right? So I can say that this is the instantaneous center of rotation for 1 and 2. right? So I can say that this is the instantaneous center of rotation for 1 and 4. Means 4 with respect to 1 is rotating, 2 with respect to 1 is rotating, right? So now what is the instantaneous center of this link 3? Is it actually in pure rotation or in pure translation? That's the question. So you have some revolute pairs here, here one pair and here another pair, right? So what is the instantaneous center of rotation of link 3? Because 3 is actually neither in pure rotation nor in pure translation. It is a mixture of those both things. So now how do we find out that general plane motion? This type of motions are called as general plane motions. So now our concept is about general plane motions. Link 2 can be seen as pure rotation. Link 4 can be seen as pure rotating member about a fixed origin, right? But 3 is having a general plane motion. So right now, let's take some link like this, and let's say that it is in general plane motion, and the velocities, let's hope that the velocities are given. Usually that is the case. So let's say that here, if you see, this is the velocity point, or I'll just say that no, this is the velocity point of that link in this manner, some way, and this is the velocity point of the same arbitrary link at another point. Like let's take the example of 3 itself. That will be easier, right? If you take link 3, it must look like this, right? I'll take the same thing and I'll project it there. So that might feel easier for you people. So let me erase this, and let me erase even this right now. And we are going to take the velocities of that point itself. See, if you look at 4, the velocity of link 3 at this corner should be in this direction, right? Perpendicular. So let's take that perpendicular over here. Better than all these things, I'm going to take the link itself. Parallel to it, let's take it to find out the velocities. Let's take one corner and this, and another corner as that. And then now, right now, I am going to take perpendiculars. See, link with respect to link 4, if you check, this is the velocity arrow, right? Just check with respect to link 4. At that point, that will be the velocity arrow for both the links. So this is the velocity arrow and direction of velocity, I mean. And at this point, I can see that this is the velocity, right? So put it here. Now what you need to do is, from the earlier concept what we have learned, I told that the center of rotation is perpendicular to the velocity vector. Okay, right? So center of rotation is perpendicular, means I can take a perpendicular in this manner over here, right? Similarly, I can take a perpendicular over this one also over here. So now I got an exact center of rotation of that link, which is this point, and it can be named as instantaneous center. It means at that instant of time, it is, this link 3 is in complete rotation, right? This link 3, you can see that it can be assumed that it is in pure rotation. I can say that it is in pure rotation about this center. Now, if I want to find out, let's label them O, A, B, C. Now, this is point A, this is point B, and this is VA and this is VB. Now, to find out the velocities, for instance, if VA is given, how to find out VB? So this, in this problem right now, you can check it out how I'm going to do it. So I can say VA is equal to R omega. Now what is R? According to our previous definition, R is the distance from the center of rotation to the point on which we need to find out. What is the center of rotation? IC is the center of rotation. From here you have to measure till point A, right? So that is the point, and it is omega. Omega is of the link 3. So omega link 3. right? And now to find out velocity of point B, you write down distance like from IC to point B and times omega 3. So omega is same in both the things. I can just equate them. VA by IC to A distance is equal to VB IC to B distance is equal to omega 3. You can take any two of these equations like this and this. If you know omega 3, you can equate it with omega 3. If you don't know omega 3, if you know VA or VB, just equate one of those and get the answer. For instance, if you know VA, if VA is known, so I can just equate it VA by IC to A distance multiplied by IC to B distance to find out velocity at point B. So this is the this is the entire application of instantaneous center of rotation. Okay, so this is the application of instantaneous center of rotation. Now guys, to find out different instantaneous centers, as we have already started, we have seen a link, right? This is a link which rotates about a point, fixed point. So this is an instantaneous center of rotation of this link, right? If a point is fixed about which it is rotating, that itself is the instantaneous center. For example, link 1 and link 2 are connected in this manner. So instantaneous center will be this point where the joint is present, where the revolute joint is present. So this is the I center of 1 with respect to 2 or 2 with respect to 1, anything when we taken, okay? And next, if there are higher pairs, if you see that a roller is rolling on a floor, right? It's a point contact, right? So the instantaneous center will be the point of contact. So this is your instantaneous center of rotation, IC, okay? So this is your IC here, this is your IC here. Let's take 1 and 2. So 1, 2, IC. So here also 1 and 2. So I can say 1, 2 with respect to 1, 2 is in pure rotation at that particular moment. And now there is another case where you can take a slider on a plane. So slider on a plane, and this is 1 and this is 2 link numbers. So now how do you think that this slider is rotating? When will it rotate about 1, or when will 1 rotate about 2? So we need to find out instantaneous center. Is it ever possible that link 1, if it is sliding, is it having a center of rotation? If a link is sliding, it means it's having a linear path. Do you think that it is rotating about a point, fixed point at that instant? Okay, for this question, we can imagine our Earth itself. Is it flat or is it spherical? Is our Earth flat or spherical? It is absolutely spherical, but at the point where you are standing, or at the point where you are walking, or whenever you go through like any plane, you see that it's almost flat, right? It's flat. So the meaning is that it is flat because it has almost infinite radius. We won't say actually infinite radius, very big radius you are having. It's having a very large radius. It's similar to this one. If you see a sphere with a very large radius. If you look at an instant, or a small point on the surface itself, see a small point on the surface, you can see that, check it here. Is it linear? Yes, it looks linear, right? It means the center of rotation of a linear member, right? It's almost infinite. It's almost infinite. That's why whenever we look at cases like this, you say that the center of rotation of slider with respect to the fixed surface is at infinity. So I can say that IC is at infinity whenever I see a member is sliding, and that should be perpendicular to the plane on which it is sliding. Okay, So these are the different things which you should know about sliding. And one more thing also is there about sliding. First, suppose you have this big circle itself. Okay, I'll take another circle for our example. Let's take this big circle. Done. And this you have a center. You have a center for the circle. Let's say that this is the center. Now, just assume that you have seen a link which is actually on this surface, like this, a small slider which is actually sliding on the surface. And let's fix it the surface. Let's fix the surface, which is the spherical surface. Now, what do you think the instantaneous center of slider would be? The instantaneous center of slider in this case will be the center of rotation itself, center of your circle itself, right? What is the reason for it? Because you can assume this slider to be rotating. Actually, it is rotating. No need to assume, it's actually rotating on the circle, right? So I can say clearly that this is the instantaneous center of rotation of 1 with respect to 2, or of 2 with respect to 1. I can just number it 1 and 2. So I can say it is 1 2. Instantaneous center 1 2 or 2 1, both are one and the same. So these are the different ways you can identify just by looking at the mechanism. You can identify the instantaneous centers. Okay, thank you.